Okay, so we are ready for first talk after lunch, and this is by Dr. Jon Wilson, and the topic of cluster algebras from surfaces. Thank you.
Okay, so thank you for the introduction and giving me the opportunity to speak. Can you hear me? Yeah. Okay, so what will I speak about? Well, everything I speak about will revolve around surfaces in some way or another. In this first lecture, we'll look at expansion formulas. So we'll kind of look at some distant cluster variable, and we'll want to express it explicitly in terms of the initial cluster variables. So that's in lecture 1. And while this is kind of a nice, cute process and construction, it actually has some kind of practical use, and this will help us find linear bases for the underlying ring. Okay? So that's lecture 2, and then hopefully in lecture 3, we can look at other constructions coming from surfaces. I mean, so far in Jacob's lectures, any surface we've looked at, it's spat out a cluster algebra of skew-symmetric type, but we know that there exists cluster algebras of skew-symmetrizable type. And so we'll look at a certain class of surfaces that can spit out cluster algebras of skew-symmetric type. And then we'll look at another class of surface, non-orientable surfaces, and we'll see that they're, like when we play the same game on non-orientable surfaces, then that structure, that cluster structure cannot be explained by cluster algebras. And we'll look to an alternative cluster structure that can explain what's going on there. Okay? So today we'll talk about expansion formulas. And it will really be about kind of the evolution of these expansion formulas, so starting in a simple case, and then, well, adding to the complexity. So we'll look at type AN. And type AN cluster algebras, we've seen already, they can be explained by triangulations of polygons. So in particular, recall the following. If we look at the n+3 gon, we can kind of equivalently be looking at a cluster algebra of type AN. And the arcs, which split into two natural categories of diagonals and boundary segments, correspond to variables, and in particular, the diagonals will correspond to cluster variables, and these boundary segments that are with us along the whole way will correspond to frozen variables. Okay, and the triangulations then goes to clusters. And these local moves flips on the triangulations correspond to mutation. Okay, and so just to fix some terminology, our arcs, if we say it is gamma, will correspond to some variable x of gamma. Some triangulation T will correspond then to x of gamma, while gamma runs over all arcs in our triangulation. Okay. And at this stage, you really should be thinking of our triangulation going to be some initial cluster, right? We're going to fix some initial cluster. So T paths. For type AN. So let's fix some triangulation, which will act as our initial cluster. So it's a triangulation of the n plus 3 gon, so we'll have 2n plus 3 things. The first n are going to correspond to the diagonals. And the remaining ones are going to be the boundary segments. Okay. So this is our kind of initial cluster. And then we want to look at some distant cluster variables. So let's pick some arc on our surface, alpha, which is not in our initial triangulation. And we put some orientation on this arc, right? And there are obviously there are obviously two ways. We pick one of them. Okay. And the thing that we're concerned with is going to be the intersection points of alpha with this triangulation T. So we can denote these intersection points by P1 up to PD, if there are D intersections. Okay, so let's just kind of draw the picture we have so far. We have some arc alpha. And then this is in our surface somehow, so it's not in our initial triangulation, so it's going to intersect the arcs in T in some way. And we're going to label these vertices from P1 up to PD with respect to the orientation of this arc, alpha, right? So we can put an ordering on them in terms of which one is closest to the start point of alpha. So the notation will be P1 less than P2, so on, less than PD. Okay. So now we can get on to the definition of T-path. So a T-path, which will always be written as zeta of the arc alpha, is a sequence of oriented arcs in T satisfying some property. So this sequence, let's say it's gamma I1, gamma I2, gamma I length of zeta. And as I said, it satisfies, or has to satisfy, some conditions. So the first one is that this sequence has to be some kind of, well, alpha has to be some kind of concatenation of this sequence. So the start of alpha needs to coincide with the start point of this directed arc, gamma I1. And then from then onwards, the endpoint of gamma I1 needs to be the start point of gamma I2, and so on and so on. And then finally, just like the starting condition, the end of this arc, I length of zeta, needs to be the endpoint of alpha. Okay. So yeah, like I said, I mean, you just need to think of this as alpha being some concatenation of this sequence of arcs. So the second condition is essentially saying in this sequence of arcs, any arc can appear at most once. Yes? Oh no, yeah. I mean, this is a triangulation as introduced by Jacob, right? It's just some maximal collection of pairwise non-intersecting arcs. Right. Yeah, so the second condition is just saying that out of these bunch of arcs, just at most one can appear. So said a different way, if j is not equal to k, then gamma ij is not equal to gamma ik. The third condition is just saying we have an odd number of arcs here. And the fourth one is a restriction on the even arcs, meaning that, okay, so when this index is even, then it has to cross alpha. There is no restriction on what happens to the odd arcs. They can or cannot cross alpha, but the even ones have to cross alpha. So gamma ik crosses alpha when k is even. And then there's a fifth condition, which I guess I can squeeze in at the bottom, which let me write it down and then I can explain what's going on. Okay. So, I mean, this is the formal description of what is going on, but this should be kind of thought of as the t-path is preserving the intersection points, right? As I go longer and longer along the t-path, the intersection points get further away from the start of alpha. Okay. Is that clear? Are you asking what's the indices down here? Sorry, I can't hear you. Zeta? You mean what is this quantity here? Oh, L of zeta, which should be, I mean, it's just the number of arcs in this sequence, right? If there were k arcs appearing, then L of zeta would be k, right? Is that clear? Yeah. Okay. Right. Okay. Yeah. But just to say, this condition is really referring to the t-path preserving the intersection points. So let's look at some examples. We'll look at the sixgon. So we look at some triangulation, and then we need to pick some arc alpha that we want to look at the expansion of. This is alpha. So we've oriented it from this vertex to this vertex, so any t-path has to start at this vertex. So we can see we have two choices here. Let's pick this top one. So this will be our first arc in the t-path. And then the second condition, the fourth condition is saying that even arcs have to cross alpha. So at this point in time, we have to choose this arc, therefore, to be our second arc. Then we have a choice over the third. Let's choose it to be this. And then we have this, that even arcs have to cross alpha, so we would have to pick this arc as our fourth one, and then we would have to pick this one as our fifth one. Okay? So this is a t-path. I mean, let's just run through. It has this concatenation property. I would say neither imply each other, right? I mean, it's just saying that, oh yeah, these intersect, oh yeah, I suppose actually maybe T5 does imply. Yeah, and then therefore it's an even arc, and it's an intersection point. Yeah. Yeah, I mean, yeah, T5 implies T4, yes. Yeah. T4, I mean, is definitely not going to imply T5. This is, I mean, I'll run through a non-example, and then we can see, right? Okay, so I mean, okay, let me finish on this one first, and then I can run through the non-example. So this is a valid t-path because it has this concatenation property. No arc appears more than once. The length is 5, so it's odd. The even arcs intersect the arc alpha, and this intersection property, I mean, this even arc, and we have this even arc, and this is appearing before this one, and the intersection point appears before this intersection point, right? Is it clear? Okay. Wait. I'll do another example of what a t-path is, and then we'll get to the non-example. So again, picking the same triangulation, same arc alpha, we're just looking at a different t-path. So let's this time start at this boundary segment. Now we have a choice, right? Our even arc has to cross alpha, but we could choose it to be this one, or we could choose it to be this one. We can choose this one. And we can go 3, then we have to go 4, and then we can go. Okay. Actually, let me choose a different one. So this was our third arc, and the fourth arc has to intersect alpha, so we could choose it to be this one. Then our fifth, sixth, and seventh, right? So, I mean, this is just showing that these t-paths can have different lengths. This is 7, it's still odd, so it's legit, and you can run through and you can see that all of the axioms are satisfied, and here we can again see that we have the intersection preserving property. Okay. So these are valid t-paths for gamma, for alpha, sorry. And now we can look at some non-example. Okay. Which is where this intersecting property will not be preserved. Okay. So let's write it in a very close t-path to this one, but that is not going to be a t-path. So here, like we said, after we go along 1, we can go along 2, but then maybe we go back 3, 4, 5, 6, and then 7. Okay, and so this is not a valid t-path because this second arc, the intersection point, is happening after after the intersection on the fourth arc, right? Oh, right, okay, you mean like this? Yeah. Yeah, sorry, this is exactly what I meant, yes, sorry. Okay, so we have this, this notion of t-path, and of course the goal is to write this, this variable corresponding to alpha. And so from this t-path, we want to spit something out, some kind of Laurent monomial out that is maybe not okay in our cluster algebra, but in our ambient field. So to each t-path zeta of alpha, we associate the following. So this Laurent monomial that we spit out will always be referred to x of zeta, and it's going to be the product of all cluster variables corresponding to the odd arcs. Times the inverse product of all of the variables corresponding to the even arcs. And we'll denote by pt of alpha the set of all t-paths of alpha. Okay. Okay, and now we can state the first theorem for these type A and cluster algebras, which is due to Schifler. Which says for any alpha that we could have picked. We have the following expansion formula for the corresponding variable. Which is going to be the sum over all of these x zetas over all zetas over all t paths of alpha, right? Okay. So we can kind of look at the simplest example to verify that this is true in at least some case. Yeah? Right, okay. Correct? No worries. Right, so our example is going to be of the quadrilateral. Okay. So this is the triangulation. We'll fix an oriented arc alpha. And we'll label these arcs from A to E. We can look at this set of t-paths of alpha. Which is easy to see, there are just two of them. Because so alpha is starting at this vertex, and if we pick alpha, then it's uniquely determined. If we pick A first, then it's uniquely determined, and when we pick B first, it's also by symmetry uniquely determined. So if we chose this to be our first arc, then we have to go along E, and then we have to go along C. And if we picked B first, then we'd again have to go along E, but in the opposite direction. And then we'd finally have to go along D. Okay, and so if we label this first t-path by zeta 1, formally this should be written as A, E, C. And then zeta 2, B, E, D. And then the corresponding variable is therefore going to be XA, XC, all over XE. X of zeta 2 is going to be XB, XD, all over X of E. And then we can write this and when we get to this expression, we instantly know that this is x of alpha by the Tolmie relation, right? As mentioned in Jacob's lectures. Okay. So this is done for type AN. And yeah, okay, I should be more specific. It's type, yeah? Oh, yeah, I mean, if you had the orientation of the arrow it's easy to you just read the t-path from back to front, and then you'd get the same thing, right? Sorry, what's going? X alpha. This is X alpha. Oh, this is just the cluster variable corresponding to the arc alpha. Right. I mean, this is just the terminology that I'm using. Right. I'm saying X gamma equals cluster variable corresponding to gamma, right? Where gamma is some arc. Sorry? So this is our triangulation, and if we were to flip the arc E, then we would get alpha. Yes? Okay. Okay, and so this expansion formula was for AN. And AN when the only coefficients we had were coming from the boundary, right? We weren't allowed to just put any coefficients. It was very specific to the surface case. Okay. But nevertheless, this expansion formula was for AN. However, we can make some tweaks to our approach to get the result for unpunctured surfaces. And we'll look at that now. Let me write the new definition here, just so it's side by side. So T1 prime was this concatenation property, and this we keep. T2 things change. Before we were just allowed to have an arc appearing just once in the t-path. And now we can have it more than once. But with the following restriction, we can't have any kind of silly cases. We can't go along the arc and then come straight back down it. And so we say that this path needs to be reduced. Okay, so let's just draw a picture of what I said is not allowed to happen. We're not allowed to go, say, k and then k plus 1. Is it clear what I mean by this? Okay. So T3 was this length must be odd, and we still keep that. We still keep that we must cross the even arcs. And we also want to keep this, this intersection preserving property as well. And we have a sixth condition, and this is because we're no longer on a simply connected surface. And it's roughly going to translate as we want this t-path to stay close to the arc alpha. Okay. So, said in a more precise way, the t-path and alpha are homotopic between any intersection points. Right, okay. And okay, so this is a, let's say, extended t-path definition. And it's pretty easy to see that when we restrict our surface to the case of AN, it will just coincide with this definition here, right? I mean, because our path must be reduced, and we have this intersection preserving property, then that would imply that no arc can appear more than once. And then this homotopic condition, I mean, is just automatically satisfied on the polygon because it's simply connected and there's only one path between any pair of points. Okay? So I'll just draw a picture for this sixth condition, and then we can state the next result. So what I mean by this sixth condition is that, so we're concerned with the intersection points Pij and Pik, so we're concerned with the arcs gamma ij and gamma ik. And then we have some arc crossing our surface and crossing these arcs. And say we've oriented these arcs gamma ij and gamma ik in the following way in terms of our t-path. And then we have some t-path between them. Okay. And this condition is saying that once we go along, we start from this point Pij, and then we just go along the t-path. And then we end at Pik. And this condition is saying that this blue arc and this red arc are homotopic, right? And sorry? So the even arcs have to intersect alpha. The odd arcs don't. Maybe they intersect, maybe they don't. Okay. Okay. Did you have a question? No. Okay. Right. Okay. And so on the, like I said, on the polygon, it's simply connected, so this is clearly satisfied. But maybe as when you go on a cylinder, this alpha might be on kind of the front of the cylinder, and then this blue arc might be on the back, and then they're not homotopic. That's the potential problem. And for this to be a t-path, we want that not to be the case. theorem. This time it's Schifler and Hugh Thomas, which was a year later in 2008. And like I said, for unpunctured surfaces, under this extended definition, we get the following expansion formula, which is, in some sense, just the same as the other one. Okay, so let's just run through an example to see how this goes. So we'll pick the cylinder with two boundary components and two marked points on each boundary component. Pick a triangulation. Then we'll look at some arc going twice around. And then we want to look at some t-path. Okay. So this is, let's orientate this arc like this. So this is the starting point. We'll choose this to be arc number 1. Then arc number 2 has to cross. We can pick 3. Four. 5. Evens have to cross, so we pick 6. And then we can finally pick 7. Okay, so we have this concatenation property. The length is odd. Even arcs intersect, and one thing we have to check is the intersection preserving property. So this would be, I guess, pi2. This would be pi4. Even though we intersect this, we don't have an even arc intersecting it, so it's not going to form kind of part of our sub-collection of intersection points. So this would actually be pi6. And then we're done, right? And you can see that intersection preserving property holds there. I could have stopped at 3. Yeah. Oh, 1, 2. So, yeah. Okay. Yeah. That is true. Yeah. But yeah, I mean, it is true that you. I mean, these paths can have different lengths, right? You can stop. Wait, so, yeah, it doesn't need to be globally homotopic. I mean, let's just let's just run through it again. So, one thing. Okay, so this. I mean, I should be saying that this really is pi0. So this is kind of like the lazy path. And then it's okay. I mean, you can stop. You can stop very early. Yeah. As long as this is okay. Yes. So yeah, okay. I should be saying this definition should be viewed where we have this being kind of the lazy path, and the last one also being the lazy path. Yeah. Okay. Exactly. Yeah. Okay, so, right, this is an example, and okay, yeah, I mean, I won't go through this, but you can check that the homotopy condition is satisfied by this t-path. Okay. And I mean, in general, you don't have to check any pair of points, you just have to check these steps of 3, right, from evens to evens, even, odd, even, right? As long as it's homotopic along that piecewise, then you'll get homotopy condition satisfied. Okay, so this is completely done for unpunctured surfaces, but as we mentioned, the only coefficients we have are coming from the boundary, and maybe we'd like to add coefficients in. A very important class, as we've seen in other people's lectures, are principal coefficients. And so, can we see this from these t-paths, right? So, what about principal coefficients? Can we read them off too? And the answer is no. And why is it no? Well, it's because this definition of t-path forgets way too much information. I mean, as Laurent said, I mean, we could really take even a much shorter t-path, and then we just forget we forget too much of the other surface. Okay, yeah. So have you not met principal coefficients yet? So I mean. Well, on the level of quivers, I'm saying so. Perhaps you would have some quiver like this coming from a surface. So these are your mutable vertices. And principal coefficients are, we're adding in a frozen vertex for each of these mutable vertices, and we're adding one arrow into that corresponding vertex, right? That's what I mean by adding principal coefficients. And okay, it hasn't been talked about, but principal coefficients can be kind of seen on the surfaces with laminations by adding a curve that slightly perturbs each of these arcs, but maybe that hasn't been spoken about. Yes. Okay. Right. But okay, does that answer your question? Yeah. So, I mean, there are two things you could do at that point, right? Yes, you do have frozen variables corresponding to the boundary, but maybe you could just evaluate them all at 1, and then so you get rid of those in that sense. Or you could just add frozen variables on all of the ones, and then also have some frozen vertices coming from the boundary, and that's also a possibility. Yes, I mean, you can do either. I mean, does that answer your question? Okay. Right, okay, yeah. So as I said, no, I mean, because currently the definition of t-path forgets too much information. And so now we're going to kind of amend this definition of t-path to something called a complete t-path, which goes in and fills in kind of the blanks in some sense, this piece of information that we were completely missing. So a complete t-path is the same kind of setup as before. So it's some collection of arcs. And really we want, in some sense, all of the axioms that we saw before. So T1 double prime is T1 prime. We want this concatenation property. T2 prime, well, is in reality, I'm going to write it down, but it's no condition, but I'll write it just to kind of compare it to the old, and just saying now there's no reduced restriction, right? This reduced condition is relaxed. We're allowed to go along an arc and come back straight back down it. T3, this was maybe talking about the length. The length is still up. So, and actually, T4, the even arcs intersecting is still there. And T5, the intersection preserving property is also still there. The thing that's going to change is this homotopy condition is going to be strengthened. And I mean, it's going to be really strengthened so that it actually, proves essentially all of the things above anyway. So what is this strengthened homotopy condition? Well, it's saying for all k from 0 to d, where d is, again, the number of intersections of alpha with the triangulation, then the segment of t-path starting at pk and then following gamma 2k, then gamma 2k plus 1, and then gamma 2k plus 2, until the intersection point pk plus 1. So this t-path, this segment of t-path is homotopic to the segment of alpha between pk and pk plus 1. Okay. So let's just give a picture to what I am talking about there, and then we'll realize how strong of a condition that is. So we have our arc alpha, again an orientation on it. And like before, we have the arcs in T that intersect it. So we have P1, P2, and then we have PK, PK plus 1, PD minus 1, and PD. Right. Okay, and so this condition that I wrote down over there is very strong because it's saying that this intersection point PK has to be the intersection point of the arc gamma 2k, and this one gamma 2k plus 2, and then the arc in the t-path connecting them is, of course, gamma 2k plus 1. But it's, I mean, what I'm saying is it's very strong because, so this kth intersection point has to be gamma 2k, right? Gamma 2k has to be that arc intersecting P of k, yeah? Oh, okay. And of course, we have this condition that when we go along pk and along this path, it's homotopic to that segment of alpha as well. Okay. So let me draw the example of such a complete t-path next to this to see how maybe you've computed all of the t-paths with this version of t-path, with this extended t-path definition, and then you'd like to get to the complete ones, right? And there's of course, there's a very simple way of doing that. And it's essentially going around and filling in the information that we missed last time. So let's look at the same triangulation and the same arc alpha. Okay, so how did we start before? Well, we went along 1, and that's absolutely fine. It's going to be 1. And then we went along 2. Okay, before we do this t-path, let's just go along and look at the order of intersection points. So this one is P1. We go along, this one's P2. We go along, so this is P3, P4, and wait. 1, 2, 3, 4. Did I draw this correctly? Yeah, I've missed this one. Yeah, sure. Okay, so yeah. This is P2. P3, P4, and P5. Okay. Right, and so, okay, yeah, we started off 1, we went 2, that's absolutely fine. This is agreeing with the definition that we have. And then we went along 3. But this is our second intersection point, right? So therefore, the fourth arc needs to cross this guy. So we need to go back along this. And then we wanted to end up where we were back, so we need to go back along it, right? So this is our fifth arc as well. This is the third intersection point, so if we chose this to be 6, it's okay, which is kind of following the same method. So 6 is now substituting for 4 over there. We can go along... no, we can't go along this next. Because this is our fourth intersection point. So our 8th arc needs to be this one. Therefore, we need to go along this arc and then back along it. Yes? So this needs to be 7, and then we need to go back along it for 8. Then we can follow it 9. And we have a 5th one, so this can be our 10th. And then finally, we'll get this as our 11th arc. Okay. And okay, yeah, so in this definition, you can see from this strong condition of T6, that the length of this will be 2D plus 1, right? And it's exactly what we get here, right? There were 5 intersection points, 5 times 2 plus 1 is 11. Yeah, of course they're in bijection. I mean, this is what I was perhaps... Yeah, I mean, they're in bijection by exactly the kind of construction that I did there. I mean, it really is going in and filling the arcs that you missed, right? Making sure that the intersection points you missed become the even arcs, and the bijection is following this process. Well, yeah, there was already, of course, there was already enough information on your surface, but there wasn't enough information in your t-path, right? Okay, so, right, so this is an example of a complete t-path, and the goal of introducing this was, of course, to introduce principal coefficients. So how are we going to do that? You know, how is suddenly this complete t-path going to be able to read off the coefficients? And we'll see that it's via the notion of alpha-oriented arcs. So. Okay. So definition, let gamma 2k be an even arc in some t-path zeta. And if it's an even arc, therefore it can't be a boundary segment, it must be a diagonal. So hence, gamma 2k is a diagonal of the triangulation. Therefore, it's the glued side of two triangles, right? Okay. So we'll draw the two possibilities here. So it's the glued side of two triangles, so this guy is gamma 2k. Okay. And alpha is crossing our surface like this, say. And the two possibilities are that gamma 2k in our t-path is orientated this way or the other way, right? So it's either like this or it's like this. And how are we going to read off coefficients is by looking at the first triangle that alpha intersects, and by looking whether this orientation on gamma 2k either agrees with the orientation induced by the surface or disagrees, right? So here, I mean, the natural thing I imagine in Jacob's lecture, the orientation that he put was a clockwise orientation. And this is therefore part of a clockwise triangle, right? I mean, and so therefore we call gamma 2k is alpha orientated, and here it disagrees, right? It's anti-clockwise. So therefore, gamma 2k is not alpha oriented. Okay. Okay. Now I can finish with the final theorem. First, we just need to realize which coefficients a t-path is spitting out. So given a complete t-path, zeta equals gamma I1, gamma I2, all up to gamma I 2d plus 1. Then we define this kind of y monomial by taking the product over all gamma, over all alpha-orientated arcs, right? The product of the y's over all alpha-oriented arcs. So it's going to be y gamma 2k, where gamma 2k is alpha-oriented. Can you still hear me? I mean, I feel like this thing's halfway up my face now, but I'm still visible, audible, sorry. Right, okay, so I'll end by giving the theorem, which is down to just Schifler again. This is 1 year later, 2010. So for any arc alpha not at t, and I should say this is for triangulation of an unpunctured surface again. We have in the associated cluster algebra for this triangulation with principal coefficients. The expansion formula. So now it's going to be overall complete t-paths of alpha. We're going to again get this x of zeta, but it's multiplied by now this coefficient term y of zeta. Okay. Right, okay, and this is the kind of story of t-paths that I wanted to speak about, and in the next lecture we'll see how this is so convenient to getting linear basis of the corresponding surface cluster algebra. But okay, that's all I want to say now. Is gamma 2k really? Sorry, is gamma 2k really gamma I? Oh, did I forget it? Yeah. It is. Yeah. I mean, sorry, I really should. I should have put I's there. Yeah, exactly. Yes. Yeah. So yeah, definitely. And I mean, I'll kind of mention that when I then go on to snake graphs, and then there's kind of a natural way of going down. It's less clean, but yes, you can come up with some kind of notion. And really, I mean, okay, I'll speak about more of it, but you would go and get a perfect matching of the snake graph, and then you would kind of translate that onto your t-path, and that's kind of the best way I know of getting there, really. Yeah. You mean in terms of whether I kind of had a silly intersection? You mean like, oh no, I mean then of course it would go wrong. I mean, you mean like in terms of if I went something like this? Yeah, I mean, because then you're just counting something different, right? Oh. Oh, in terms of whether this complete t-path definition is robust enough. Okay. It probably is, yeah. I mean, because of just this strong homotopy condition in terms of it would just make you just go up and down. The other t-path definitions I gave, of course, this would go wrong, right? Because, but in the complete one, yeah, I think it would just force you to go up and down, and then it would. But the thing is, it would go wrong in terms of the level of this. Yes. Yeah. Mm-hmm. Okay. Yeah. If you then put all coefficients to 1, then I'm almost sure you get the cluster variable. Yeah, because you would just be going up and down from this strong homotopy condition. Exactly. Yeah.
Any more questions? If no more questions, let's thank the speaker again.